Welcome to a lesson on simplifying radical expressions. First, we'll take a look at simplifying radicals that don't involve fractions. A radical is not simplified if the radicand, or the number underneath the radical, contains perfect nth root factors. So what that means is if we have a square root, we can't have any perfect square factors under the radical. And if we have a cube root, we can't have any perfect cube factors under the radical if it's in simplified form. So here's how we'll accomplish simplifying radicals. We're going to write the prime factorization of the radicand. Then we'll circle the nth root factors, which means we'll circle the equal factors in groups the same number as the index. The circled factors are the perfect nth roots that can be simplified, and the factors not circled will remain under the radical. And then once we do this, we'll rewrite the radical in simplified form. Now, one thing we do have to remember, if the index is even and the radicand has variables that simplify, we do need to include an absolute value around the simplified variables with odd exponents to assure the variable is non-negative. Let's take a look at some examples. If we want to simplify the square root of 50, remember the index would be 2. We're going to write this out in prime factored form. 50 is 2 times 25, and 25 is 5 times 5. Since the index is 2, we'll circle the equal factors in groups of 2, as we see here. This is a perfect square factor of 50, and therefore this will simplify. The square root of 25 would be 5, and we're left with the square root of 2. So what you'll notice is every time we have a group of equal factors, it'll simplify perfectly to just one of the factors outside the radical. Number 2, we have the cube root of 64. So we'll write out the prime factorization of 64. I know 64 is 8 times 8, and 8 is 2 times 2 times 2. So there's 8, there's another 8. So that would be 64. Again, the index is now 3, so we'll circle groups of 3. There's a perfect cube factor, and there's a perfect cube factor. Well, the cube root of 2 cubed would be 2 from this group, and then the cube root of 2 cubed here would also be another 2. Well, 2 times 2 is equal to 4. The cube root of 64 equals 4. Again, notice we're taking one factor from each group that we circle. Okay, let's go ahead and try two more. Now we have some variables, so we do have to be aware we may need an absolute value on the part that simplifies. Let's go ahead and write out the prime factorization. 8 is equal to 2 times 2 times 2. We have 4 factors of x, 7 factors of y. This is a lot of writing, but I think it is worth it when we're first learning how to do this. Because the index is 2, we'll circle groups of 2. Remember, the circled factors represent the perfect square factors of this radicand. So when we simplify this, this will be 2. We'll have a factor of x from this group, another factor of x from this group. That would be x squared. Notice that we have a factor of y from here, here, and here. That would be y to the third. And then we have the square root of 2y. Notice the 2 and the y were not circled. Now, because the index is even, and this has an odd exponent, to assure that this, we do need to take the absolute value of this. So we could take the absolute value of y cubed, or we could take the absolute value of 2x squared y cubed. It really depends on the textbook. Okay, let's go ahead and try number 4. 64 is 6 times 9, 6 is 2 times 3, 9 is 3 times 3. Look at the variables this time. We know we want groups of 2. So instead of writing 3 factors of a, I'm going to write a squared. There's a group of 2 factors of a times a. And instead of writing out b to the 10th, I'll write out b to the 2nd 5 times. This saves us some writing as long as you can remember that each of these is a group of 2. So there's a group of 2, there's a group of 2. There's 5 groups of 2 for the factors of b. So what does this simplify to? We have a factor of 3a, b to the 5th, and we're left with the part that doesn't simplify, which is 2a underneath the square root. We have an even index and some odd exponents, so we do have to have the absolute value of 3a b to the 5th. Okay, let's take a look at all types of radical expressions. All of these statements must be true in order for a radical to be in simplified form. All possible nth powered factors have been removed. We were just working on that. Number 2, no radical contains a fraction. And then number 3, no denominator of a fraction contains a radical. Let's take a look at some examples of this. For number 1, we're not allowed to have this fraction underneath this square root. Well, we can rewrite this as the square root of 9 over the square root of 25, but now we're not allowed to have the square root of 25 in the denominator. But luckily, the square root of 25 simplifies perfectly to 5, and our numerator would be 3. So we're okay on this one. But number 2 is a little bit different. If I rewrite this as the square root of 4 over the square root of 5, we can't have the square root of 5 in our denominator in simplified form. So we have to think to ourselves, what can we do to this so that it simplifies perfectly? Well, if we had 2 factors of 5, it would simplify perfectly. So what we can do is multiply by the square root of 5 in the denominator, as long as we do the same to the numerator. The reason we want to do that is because our denominator is now the square root of 5 times 5, and our numerator is the square root of 4 times 5. This is great because now our denominator simplifies to 5, and our numerator would be, well, the square root of 4 would be 2, so we'd have 2 square root of 5. Let's look at another example. Now we have the cube root of 2/3. This is equal to the cube root of 2 over the cube root of 3. Now, in order for the denominator to simplify perfectly, we're going to need 3 factors of 3. So we can go ahead and multiply by the cube root of 3 times 3. That'll give us 3 factors of 3, which matches the index. So I'm going to do the same in the numerator. So now we would have the cube root of 3 factors of 3, which is perfect, over the cube root of 2 times 3 times 3. Again, we're only concerned about having the radical in the denominator. We don't care if it's in the numerator. So here's our group of 3, so our denominator equals 3, and our numerator would be the cube root of 18. Let's try one more. This is about as challenging as it'll get until we introduce the idea of conjugates. So this is equal to the cube root of 7 over the cube root. I want to look at this in factored form, so I'll write this as 2 times 2 times x times y times y. Remember, since the index is 3, we want 3 factors of 2x and y in the denominator. So we need 1 more factor of 2, 2 more factors of x, and 1 more factor of y. Of course, the same in the numerator. So what would this leave us with? In the numerator, we're going to have 7 times 2 times x times y. Our denominator now is going to have 3 factors of 2, 3 factors of x, and 3 factors of y. And that's exactly why we multiplied by this. You can see 3, 3, and 3. So this simplifies perfectly. Our denominator is going to be 2xy. And our numerator will be the cube root of 14x squared y. Now, even though these exponents are odd, we don't need absolute value around this because the index was odd to begin with. It's only when the index is even that we have that special rule. Okay, I hope you found this video helpful. Thank you and have a good day.